begins with a breath, not of life but of death. A massive star, swollen and unstable, exhales with violent intensity, shedding layers of its own body into the cold vacuum of space. This isn't the gentle wind of a dying ember. It's a storm of matter, more than twice the mass of our sun, expelled in a final act of stellar desperation. What it leaves behind is a cocoon, a thick, turbulent shell of gas and dust wrapped around a ticking time bomb. And then silence. A pause. A moment before the end. Then detonation. The core of the star collapses in on itself, unleashing a supernova, one of the most violent and energetic events in the cosmos. In the blink of an eye, it releases more energy than our sun will emit in its entire 10 billion year lifetime. But the true power of this event isn't in its light or heat. It's in its invisible impact. According to a new study accepted for publication in Astronomy and Astrophysics in May 2025, supernovas can become nature's most powerful particle accelerators, if the circumstances are just right. These rare events, known as PeVatrons, are capable of launching subatomic particles to energies exceeding 1 quadrillion electron volts, PV. That's not just powerful. That's 1,000 times more energetic than the collisions produced at the Large Hadron Collider, the most advanced particle accelerator on Earth. This finding helps unravel a mystery that has puzzled astronomers for nearly a century: the origin of ultra-high energy cosmic rays, particles so powerful they seem almost unnatural. Since the early 20th century, scientists have detected strange, high-speed particles raining down on Earth from outer space. These cosmic rays are mostly protons, occasionally heavier atomic nuclei, and they come from sources we've never been able to pinpoint with certainty. While many are deflected or absorbed by Earth's protective magnetic field and atmosphere, some do manage to make it all the way to the surface. Roughly once every second, a cosmic ray passes through your body, harmless but mysterious. The vast majority are low to moderate energy, but a small fraction are extreme outliers, carrying energies that boggle the imagination. These PV-class rays have more energy packed into a single proton than a professional baseball pitch or a speeding bullet. They're subatomic warheads, and yet, for all our instruments, satellites and observatories, we've never directly caught the exact moment or place of their birth. Supernovas seemed like obvious suspects. They're violent. They're common. They generate immense magnetic fields and particle storms, all the right ingredients for acceleration. But the numbers didn't add up. Observations of nearby supernova remnants, like Cassiopeia A and Tycho, revealed cosmic rays, sure, but none anywhere close to the PV range. So the mystery deepened. If supernovas weren't the source, what was? Enter the new research which doesn't reject the supernova hypothesis, it rescues it. The key lies in what happens before the star explodes. To become a PeVatron, a supernova must erupt into something dense, not empty space. The star needs to shed mass, at least 2 times the mass of our sun, and that material must linger close by, forming a tight, thick shroud. This happens during the final throes of a massive star's life. Intense radiation pressure and unstable fusion processes blow off the outer layers. In some cases, these pre-supernova winds are so extreme they resemble a slow-motion detonation happening years before the real explosion. Then comes the main event. The core collapses and sends a shockwave surging outward. This shockwave collides with the dense shell of previously ejected material, and that's when all hell breaks loose. The impact drives magnetic fields to unprecedented strengths. Think of them as cosmic trampolines. Charged particles bounce back and forth across the shock front, gaining energy each time. This process, known as diffusive shock acceleration, can amplify a low-energy particle into a PV-class cosmic ray in a matter of moments. This is where nature outclasses human engineering. Our best particle accelerators are miles long and require massive superconducting magnets. A supernova does it with raw physics and chaos, needing nothing more than gravity, plasma and turbulence. What's more, the magnetic fields generated during this shock interaction are orders of magnitude stronger than those present in typical interstellar space, and they arise spontaneously as a result of instabilities in the plasma. The feedback loop is elegant and deadly. Particles stir up turbulence, which strengthens magnetic fields, which accelerates particles even faster. It's a runaway engine of energy transfer, lasting just long enough to fling cosmic rays to their upper limits. These cosmic rays, now supercharged, are blasted out into the galaxy at nearly the speed of light. For a brief moment, that supernova becomes not just a stellar corpse, but a natural particle collider, flinging matter outward with power no human machine can rival. However, this PeVatron phase doesn't last long. As the shock wave spreads, it slows. Within just a few months, the magnetic amplification fades. Acceleration continues, but only at lower energies. The PeVatron shuts down, the window closes, and the system becomes just another supernova remnant. Impressive, but no longer extreme. This explains why we haven't caught one in the act. The last nearby Milky Way supernova visible from Earth was SN 1987A, which occurred over 30 years ago in the Large Magellanic Cloud, still a bit too far for detailed PeVatron observation. Most supernovas in our galaxy are too distant, obscured, or simply missed during their critical months of maximum acceleration. We've been looking at supernovas in their afterlife. To see a PeVatron in action, we'd have to catch the event within weeks, or even days, of the explosion. It's a narrow observational window in a very big sky. Fortunately, we're entering an era where that's becoming more possible. Surveys like the Vera C. Rubin Observatory's upcoming Legacy Survey of Space and Time, LSST, combined with real-time alerts from space telescopes and ground-based arrays, may soon allow us to detect newborn supernovae fast enough to witness this elusive PeVatron phase. And when we do, the consequences could ripple across multiple scientific domains. These early detections could offer not just particle physics insights, but windows into the chemical enrichment of the universe, shock-driven star formation, and perhaps even clues to the origins of magnetic fields in galaxies. The implications go far beyond particle physics. PeV cosmic rays influence the chemistry of interstellar gas, contribute to the ionization of dense clouds where stars are born, and may even shape galactic ecosystems in ways we don't yet fully understand. Some cosmic rays wander through the galaxy for millions of years before striking something, a planet, a spacecraft, or a detector here on Earth. Others may trigger atmospheric cascades that affect cloud formation, or in rare cases, interfere with electronics on satellites. Some researchers even propose that cosmic ray showers over geological timescales could influence mutation rates and evolution on Earth, although this remains speculative. And it all comes from a single moment, a star's explosive death, supercharged by the very matter it cast off in its final breath. In a sense, PeVatrons don't just hurl particles, they seed the universe with high-energy messengers, carrying information across vast cosmic distances. Every time one reaches us, it tells a story of violent creation, of a star that died so spectacularly it pushed matter beyond the known limits of energy. So, how many of these stellar particle colliders are out there right now, revving up in the dark? How many are preparing their final breaths, shedding their mass into surrounding space, counting down to a detonation that might change the fate of the surrounding galaxy? And how many of those PV bullets are headed our way, invisible, silent, but packed with the secrets of dying stars? One day soon, a supernova will explode close enough and early enough for us to watch a PeVatron be born in real time. When it does, we'll be ready. Until then, the sky hides its secrets well. So keep looking up, stay curious, and subscribe to this channel for more discoveries from the edge of the universe, where stars die violently and physics is pushed to its cosmic limit.